Well, hi everyone. My name is Diego Pallero. I'm a PhD student from Universidad de La Serena, working under the supervision of Facundo Gomez as part of the group of galaxy formation and evolution. The talk is titled "The Importance of Low Mass Clusters for Satellite Quenching in the CEAGLE Simulation" and are part of my latest results of my thesis. The idea is to trace the quenching history of satellite galaxies in the clusters available from the EAGLE simulation. So as many of you already have stated, the quenching of the galaxies is the moment when the galaxy cease their star formation, but it's rather a complex phenomenon. It depends on the condition of a galaxy from a satellite or central, of the mass of the galaxy, in the environment in which the galaxy resides, and also changes with time. So it's rather difficult to look for a dominant mechanism. Moreover, even inside galaxy clusters, which are the densest regions in the universe, there is different mechanism acting at different scales. For example, at the outskirts of clusters, but the local density is lower, not the same mechanism are acting, for example, at the core of the semi-cluster. So we wanted to use this hydrodynamical simulation in order to trace the evolution of the satellite population and to characterize which one is the main mechanism producing the quenching of the star formation. So the CEAGLE project are a suite of 30 galaxy clusters simulated in a zooming fashion with high resolution. We have a mass resolution around 10 to the 6, similar to, for example, the TNG 100 are the EAGLE simulation. But we have clusters ranging from 10 to the 14 solar masses to 10 to the 15.4 solar masses, and a temporal resolution from around 500 megayears, and are full physics. So they have recipes for star formation, aging feedback, star formation feedback, black hole growth and accretion. So they are the perfect laboratory to understand how, for example, the different massive clusters could affect the evolution of galaxies inside them, and also to trace these massive structures until high redshift, for example, redshift 1, and to understand how the different environmental processes change with time. And so we define here galaxies as all those structures with a stellar mass greater than 10 to the 8, and we make sure that they have at least 1,000 dark matter particles in order to be well resolved. We define galaxies quenched as when they possess a specific star formation rate lower than 10 to the minus 11 per year, in a similar fashion to what was done by other authors like in 2012. So the first thing that we want to do is to look if the pre-processing or the pre-quenching is the dominant population of clusters at redshift 0. So here you can see how the dominant population changed from in situ quench, or galaxies that reach this threshold in specific star formation rate inside the clusters that we are studying, or pre-quench or pre-processed, those galaxies that cease their star formation before their accretion into the cluster. We define the accretion time, or the accretion moment, when galaxies crosses the R200 of the cluster for the first time. And we plot the distribution of the dominant population against the M200 of the cluster at redshift 0. So here you can see that in the case of low mass clusters from around 10 to the 14, the dominant population corresponds to the galaxies that get quenched inside the cluster. So the pre-quenching or the pre-processing is not that dominant as, for example, for high mass clusters around 10 to 15, for example, like a coma cluster. So as we are looking to more massive structures, the pre-processing and the pre-quenching start to taking a more important labor into the fraction of passive galaxies that we're looking nowadays. Around 10 to the 14.6, or 5 times 10 to the 14, the population changed from in situ dominated to pre-quench dominated. If, for example, if we characterize the evolution of the population as a function of their accretion time, we can see that around the moment when galaxies crosses the period radius of the cluster first time, the fraction of quenched galaxies grows dramatically. So in this plot, you can see how the fraction of quenched galaxies grows as a function of their accretion time Here, negative values stand for the moments of galaxies before their infall to the final clusters, and positive values stand for those moments that the galaxy had already spent inside the cluster. Zero stands for the moment when the galaxy crosses the virial radii of the cluster for the first time. And each line represents one cluster and are color coded by the mass at M200. So, for example, here the blue values stand for low mass clusters, and the fraction of frequency is really low until the moment of their accretion, around 20% of the galaxies. But after their accretion time, in a time around 1 and 2 gigayears, the fraction of quenching grows from 20% to almost 80%, so which is a lot. But on the other hand, massive clusters already have a really quite massive, high fraction of massive galaxies, around 80% of, in some cases. But after 40 years, that galaxies spent inside clusters, almost all galaxies get quenched, which is expected. But we wanted to show here is that in general, the quenching of star formation is happening mainly in these low mass kind of structures. For massive clusters that we're looking nowadays, there are no much quenching happening there, even though that the environment is more beneficial for the quenching over the run pressure. This is highlighted when you, for example, resample uh, our clusters through different redshifts. And if here you can see the evolution of the quenching fraction while looking at clusters at redshift 0, 0.3, 0.5, and 0.9. And as you can see, high redshift around 1, regardless of the mass of the cluster, most of the galaxies get quenched inside of them. So, for example, the most massive clusters that we have at redshift 1 are around 5 times 10 to the 14. And if we compare the evolution of that kind of cluster with one of the same mass at redshift 0, we can see that the fraction of pre-quenched galaxies is lower at high redshift. And we ask why, and the reason is because when we're looking at clusters at high redshift, we usually look of galaxies residing for the first time in a massive halo. But when we are looking at clusters at redshift 0, they usually already have spent time in another massive halo, like a group of galaxies or a low mass cluster. So the different assembly history that galaxy clusters have at redshift 1 and redshift 0 are different, and that produces a different fraction of frequency and a different fraction of preprocessing. So the takeaway message from this plot is if you're looking for the moment when galaxies are getting quenched, you have two choices: or look for low mass cluster at low redshift, or you look for any cluster at high redshift, because it's probably that galaxies have spent all the time residing in a massive environment in that the one that you're looking. So we wanted to know also if what is the main mechanism behind this quenching of star formation. And in 2019, Ian Roberts published this paper where he proposed a lower threshold in density for the quenching to happen. And they argue that it's associated with a run pressure spreading scenario. They put this threshold around 10 to the minus 28.3 grams per cubic centimeter. And if you can see in this plot, is that the quench fraction for low mass galaxy after this threshold grows dramatically, and it's not that enhanced for more massive galaxies. So, for example, in our clusters, if we look for the gas density profiles, we can see that the threshold proposed by Robert is reached around the virial radii of the cluster, where we are looking this enhanced in the quantum fraction. We also can see that low mass cluster, which are sent here for the blue lines, possess a more extended envelope in cluster-centric normalized distance, which is more evident here in the normalized plot. The black dashed line here stands for the direction proposed by Roberts. And if we look at the local density at the moment of quenching in general for all galaxies, regardless of the condition of in situ quench or pre-process, this quenching tends to happen in environments more dense than what's proposed by Robert. So the main question and the final question is a run pressure spreading scenario what is quenching the star formation. So on this plot, you can see the evolution of the quench fraction in the right panel as a function of the accretion time, and in the left panel, you can see the evolution of the round pressure dominated fraction as a function also of the accretion time. And what you can see here is that at the moment when galaxies become round pressure dominated, that rapidly become quenched also. So in a statistical manner, we can assure that the round pressure is what is producing the quenching of the star formation. If the round pressure is high enough, the galaxies get quenched in a short time scale from around 500 to 1 gigayear. And if it's high enough to prevent the accretion of cold gas, then an observation scenario become dominant, and in a time scale of 2 to 4 gigayears, the galaxies finally get quenched. So I leave you with my conclusions. If you have any comments or any question, please ask. Thanks for your time.